Chapter 3, Subspaces of Rn and their dimensions. This is where a lot of really interesting things start to happen in this course. In section 3.1, we will be talking about the image and the kernel of a linear transformation. These two concepts, image and kernel, actually tie quite well together with previous concepts from functions. When we were studying functions, one of the things we studied was the zeros of a function. So what are the values of x such that f of that x equals 0? This is going to correspond to the kernel in linear transformations. So what are vectors x such that the matrix A times x equals 0 for that linear transformation? And the image is similar to the range. When we had a function y equals x squared, for example, we could say that the image or the range was all values y greater or equal to 0. It is similar for the image of a linear transformation. It is all the vectors that are actually reached by the matrix. So all the outputs that are possible using the matrix that is given. So the objectives are to find and interpret what the kernel is in a geometrical context, as well as by using the matrix, and likewise finding and interpreting what the image is of a linear transformation in a geometrical context or given by the matrix. We will express these, kernel and image, with spans of vectors. This is a new term that we will discuss in section 3.1. I'm going to break this screencast into two parts. The first part is going to be all about the image, and the second part is going to be all about the kernel. So let's start with the image. So the image of a function, or the range of a function, consists of all the values the function takes in its target space. It is written im of f or im of t when we talk more specifically about linear transformations. So we will write im t equals a lot. As I said, this is equivalent to what we noted as the range when we were studying functions in previous classes. Here's an example. Let's say we have a function f of t, where t is a real number, such that f of t equals a vector cosine t sine t. So it's a function that goes from r to r squared. Well, the image is, if you think of it in terms of vectors, all the vectors whose endpoint is on the unit circle, and so we would kind of blend these two notions and say just that the image is the unit circle. What is the image of the linear transformation t of x1, x2, x3 equals x1, x2, 0? We have to be a little careful here, even though it feels like we might be splitting hairs. The original space is R3. We have a vector in 3 dimensions, and the target space is also R3. We also end up with a vector in 3 dimensions, so it would be wrong to say that the image is R2. The image is the xy plane in R3. So we started with any vector in R3, and the result, any possible output, is going to be in the xy plane, but we are still working in R3. It's different than if the output was just the vector x1, x2. Then we would say that the output is R2. The image, is R2. So after looking at two examples where we have to think in the context of geometry, here's an example where we are given a matrix. So we have a linear transformation, t of x equals a x, and it goes from R2 to R3. So we input a vector in R2 and the output is in R3. What are all the possible outputs for this linear transformation? What is the image of this linear transformation? So let's check. If we select a general vector xy and we proceed to do a times x, we have a times x equals the matrix times xy equals x plus y, x plus 2y, x plus 3y. We can split it into two vectors, and the last step is the most important to understand what we're doing in this exercise. it is to factor out the x here and the y here. Why is that so important? Because this here shows us something very crucial. It shows us that all possible output vectors for that linear transformation are such that it's a certain number of this vector, so a, let's say, times this vector, plus any number of times that vector. What are these two vectors? Well, it happens to be exactly the columns of matrix A. And this is essential understanding. So the image in this particular example is a plane that is spanned by the vectors 1, 1, 1 and 1, 2, 3. In general, what we will see in a minute is that the image of a linear transformation is the span, as we will see just below, of the column vectors of the matrix. So it is quite easy to figure out what the image is when we have a matrix, at least if we don't worry about having redundant information. So I used the word span already a couple times. What is the span? The span is the set of all linear combination of the vectors at hand. So the span of vectors v1, v2, v3, etc. is the set of all linear combination of those vectors. So it's any times v1 plus any times v2 plus any times v3 and so on. What are all the vectors that we can make by combining v1, v2, v3 and so on? So the theorem that I hinted to, the image of a linear transformation t of x equals a times x is the span of the column vectors of A. If we write a matrix A by using column vectors, so we have v1, which expands up and down, we have v2, which comes from high up and goes down, v3 all the way to vn, then t of x equals a times x equals that matrix A times the vector x, which is equal to x1 v1 plus x2 v2 plus x3 v3 plus blah 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 plus xn vn. So this is very explicitly what the span of the vectors vi is. We can take any number of v1, add any number of v2, add any number of v3, v4, vn. This is really what the span of the vectors v1 to vn looks like. So the image is all the linear combinations, or the span, of v1 to vn. We're going to discuss now two key properties of the image. The first one, the zero vector in Rn is in the image of T. This Rn refers to the fact that this linear transformation in this example goes from Rm to Rn. It might not be the same. It might not be the same space, and it's a key understanding to realize that the image is something that happens in the target space. So just like the range for function, the range is not something about x, it's something about y. It's the y values that are reached by the function. Here, the image is the vectors that are reached by the linear transformation in the target space. So there is always a way, this is another way to interpret it, to have 0 as the output. We need to show that there always exists a vector x such that t of x equals 0. In fact, it's very easy, because if we choose x equals 0 in the original space, then the output in the target space is always 0, because t of 0 is a times 0, and a times 0 is 0. So we have just shown that 0 is always part of the image. Second property, if v1 and v2 are in the image, this is given, then k1 v1 plus k2 v2 is also in the image for any scalars k1 and k2. And that is said to be its closed under linear combination. This means that if you know something about a certain vector, you can multiply it by a scalar and it will still be true for that vector. And you can also add vectors together that have that property, and this sum of vectors will have the same property. So you cannot kind of fall off of the property that you're standing on. So how are we going to show that? we're going to start with knowing that v1 and v2 are in the image. That means that there exists a vector u1 and a vector u2 such that t of u1 equals v1 and t of u2 equals v2. This is because we know v1 is in the image, so there is a vector such that it reaches v1. And there's also a vector such that it reaches v2. Now, for k1 v1 plus k2 v2, we can use some of the properties that we've seen in sections 2.1 and 1.3 to say that it is equal to k1 times t of u1 plus k2 t of u2. Well, this comes from right above here, but now using the properties that I mentioned from sections 1.3 and 2.1, this is equal to t k1 u1 plus t k2 u2 equals t of k1 u1 plus k2 u2. So we've reached what we wanted. We've been able to show that k1 v1 plus k2 v2 is the image of something. That something is this vector right here. So this vector is the one we need. Its image is k1 v1 plus k2 v2. So this is where I'm going to stop for the first part, which was all about the image, and the second part would be all about the kernel. Thank you for listening.